Today we're still using our sine, cosine, and tangent ratios. We're just adding the extra step of having to read the story problem and create our own diagram. So we're calling these word problems of trig ratios, but we have a couple of new vocabulary phrases to introduce first, and then we have these 4 examples. There's our trig ratios we learned from the previous lesson. Your sine ratio is the opposite side over the hypotenuse. The cosine ratio is the adjacent side over the hypotenuse, and your tangent ratio is the opposite side over the adjacent, right? So there it is for just quick reference. That is our magic phrase. We call that our SOHCAHTOA, and that's helping us to memorize what ratio belongs with the sine, the cosine, and the tangent name. Okay, first of all, we're going to encounter situations with either the angle of elevation or angle of depression, and you realize this is not a full triangle, but if you have an object that is above you, like this hot air balloon is above this person who's standing on the ground, then you could think of this person as looking upwards. They're elevating their gaze. So this angle here is touching this horizontal line. So in both of these kinds of angles, when you're talking about this kind of elevation and this angle of depression and this angle of elevation, you absolutely must have a horizontal reference line because you are looking upwards from that horizontal line. Or in this case, you are looking downwards from a horizontal reference line. In the second case, pretend that you, the observer, is in the hot air balloon and you are dropping your gaze. So if you are depressed, you look downwards, right? So you are dropping your gaze from this horizontal reference line downwards. So notice we have 2 horizontal lines. You have this ground line. Let's say this object is on the ground and you're looking down at it. This top horizontal line is not really there. It's just a reference line that creates 2 sides of our angle. In each case, we have to turn that into a triangle. So since we already have the ground line and we have the sight line, what we need is the height of the object above the ground. So that would create our third side of the triangle, and that would be where the right angle belongs. And the angle of elevation, that is your reference angle, which means the ground is your adjacent side, and opposite that angle of elevation is the opposite leg. And opposite the right angle, there's your hypotenuse. Now, in this case, when we're dropping our gaze, we already have the ground line. We're going to use the ground as one of our sides of the triangle, and we have this sight line. So again, what we want is this height. So we're going to create this height of the object, this observer, this hot air balloon above the ground, and where that height touches the ground, of course, that's your base. The issue is, what do we do with this angle of depression? Because this angle of depression is actually outside the triangle, and we want our triangle to be here because that is where the ground is located. All right. So in a case like this, let's throw in some numbers as a quick example. Let's pretend that this angle of depression was 20 degrees. Let's just say, for instance. All right. That angle is outside the triangle. We can't use that angle here. We need this angle that's right next to it. And you might remember that this vertical height in this horizontal reference line forms a right angle up here as well. So that means these 2 angles have to add up to 90 degrees. So this would be a 70-degree angle. So if this is our reference angle, for instance, 70 degrees, and that means the height is the adjacent leg. Opposite the 70 degrees is the ground. That would be your opposite leg. And then opposite the right angle is your hypotenuse. Now, all of that is if we're using the 70-degree angle as our reference angle. You could, if you want, find this angle instead and use that as your reference angle, but I'm just showing you that from that given information with the angle of depression, you work inwards to find the angle on the inside of the triangle there like this. So we'll see that a couple times below. So let's take a look at a couple of word problems here. And our goal is to sketch the situation, label the sides, and identify what trig function we need to use. Examples 1, 2, and 3 are what I call standard problems, Example 4 is much harder. We'll have a lot more going on in that last example, so stay tuned with that. Example 1 says you are at the top of a roller coaster, 100 feet above the ground. The angle of depression is 44 degrees. About how far do you ride down the hill? All right, so we've seen this technique before where we're labeling a lot of the features, like what each side represents. So this side of my triangle is representing the ground, okay? We're going to have this roller coaster, and even though it goes up and down and up and down, let's say you're just kind of looking at a part of the roller coaster where here you are, at the top of the roller coaster, and you're going to be riding downwards, right? So this is the roller coaster track. And so this is going to be your height above the ground. And it says that you are at the top of this roller coaster 100 feet above the ground. So we know the height is going to be 100 feet. And now we bring in this angle of depression. The angle of depression is 44 degrees. So you are up here and you are looking downward at the bottom of the track. And we have to put the angle of depression in the right spot. Now you have to be careful. It does not belong here. You might think it does, but it doesn't. What we saw in that little illustration above is you have this imaginary horizontal reference line. You always need a horizontal reference line so that you can then drop your gaze. If you were to look straight out, you just see blue sky, but you drop your gaze 44 degrees, and that is the angle. It's on the outside of the triangle. We don't want that angle. We want this angle on the inside of the triangle. And again, this is a complementary pair, meaning they add up to 90 degrees. So 90 minus 44 is 46. I'm going to use that 46 degree angle as my reference angle. So now we have to label all of our sides. Opposite this right angle is the hypotenuse. The 46 degree angle right here is touching the height, so that's the adjacent leg. And then the 46 degree angle is opposite from the ground, so that's the opposite side of the triangle. So the question is, about how far do you ride down the hill? So that's not talking about this height, and it's not talking about the flat ground. Think of it like this is the path of the roller coaster down the hill. In other words, how far do you ride down the hill means we have to find the hypotenuse. All right, so we want to find the hypotenuse of the triangle there. So what that means is we're going to identify the two sides of the triangle to create our ratio, right? So we have the 100 feet, so we got to use the adjacent side. And based on the question, we have to find the hypotenuse. So these are the two sides that we got to use, the adjacent leg and the hypotenuse. You can see the adjacent leg and the hypotenuse are bundled together here behind the letter C for cosine. That means we want the cosine ratio. All right, so cosine of the reference angle, for not the original 44, right? That 44 degrees was outside the triangle. You want the 46 degrees. Cosine of 46 degrees is the adjacent side over the hypotenuse. And I'll just call that x because that's our variable right now. The variable's on the bottom, which means we set up this proportion and we cross multiply. So you have x times the cosine of 46 equals 1 times 100. All right, and so now our variable is out of the denominator, but it's not by itself yet. X is still being multiplied by a value. So we're going to divide that away. So we're dividing both sides by cosine of 46. All right, that's how we get our variable by itself. That's what we're going to type into our calculator. And just remember, your calculator has to be in degree mode when you do this. So there's the 100 divided by, call it the cosine of 46. And that should give us our answer here. So in this case, I'm rounding to 2 decimal places. So it's about 143.96, and don't forget the units on these story problems. That'll be feet in this case. So we're saying that the hill is about 143, almost 144 feet when you are 100 feet in the air with that angle. Let's take a look at a couple other situations. Here in example number 2, we've got a railroad crossing arm that is 20 feet long, and it is stuck with an angle of elevation of 35 degrees. Okay, how high is the arm from the base? Let's again draw that diagram. So what you notice here is, though, even though we have our ground as a reference line, this is not going to be a side of the triangle because there's usually some sort of a post here, and on that post, that's where you have this arm that goes up and down like this. So if it were in its down position, it would actually be here, which is not on the ground. It would be right here if it were completely lowered, and if it were completely up, it would be in this position here. Well, our railroad crossing arm happens to be stuck in this angle of elevation. So let's elevate the arm 35 degrees, and so this arm is now located here, and since we've elevated the arm upwards, that's our 35-degree angle. So the arm is not in this horizontal position anymore, but I'm still going to use that as part of my triangle, so I'm going to create a solid line for that. So this is the arm that is 20 feet long. Right, so again, this is the technique that we've talked about before, where you are labeling the name of the item so that we can see what it is, what the side of the triangle is representing. So this is the empty side, so we have to close that off to create a triangle. So from the end of that arm, bring a vertical line down. There's your right angle. So let's label our sides. Opposite that right angle is the hypotenuse. Then we have our reference angle of 35 degrees. Opposite that 35-degree angle is the height. That's your opposite leg. And this bottom side of the triangle, that is your adjacent side. So we have to figure out what exactly are we trying to find. Are we trying to find the length of the adjacent side? Or are we trying to find the length of the height here? So how high? So we're talking about height right there. So we want to find the height. So it says, how high is the arm from the base? This is the base of the triangle. So we're talking about from the tip of the arm to the base of that triangle. We're going to find the height, which means we have to find the opposite side of the triangle. All right, so we have to find the opposite side of the triangle. We have to use the 20 feet because that's information that's given to us. That'll be the hypotenuse. So we're going to use the opposite side and the hypotenuse together. So that opposite and hypotenuse are the sine ratio. So let's use sine of 35 degrees equals the opposite side over the hypotenuse. So again, I'm just using x for the variable to represent that missing side. Set up a proportion and cross multiply. So 1 times x equals 20 times sine of 35. And that's what we'll type into our calculator because our variable is already by itself. No more algebra is needed. We go right to our calculator at this point. And again, we're rounding to 2 decimal places, and don't forget the units. Here is example 3. This time we have a kite flying 150 meters in the air, and the string you are holding makes a 40-degree angle with the ground. What is the horizontal distance from you and the kite? And how long is the kite string? All right. So again, here's the ground, and here you are. So even though you would be typically holding the string and that would, create that part of the triangle, we want to abstract this a little bit. We're going to put this bottom corner of the triangle here, and let's say this is the string. So in the picture, it doesn't look like you're holding the string, but we're just saying you are located at this point, and we want the string to come together to the ground, so we have this angle of elevation. So here's your kite. And it says it is flying 150 meters in the air. Right, so that's not the length of the string. 150 meters in the air means it is above the ground, in the air, at a height of 150 meters. All right, so we're in meters now, not feet. And the 150 is describing the height of that kite. The string you're holding makes a 40-degree angle with the ground. So where does the 40 degree go? Well, it has to touch you and it has to touch the ground. So you can't put the 40 degrees here because that's not touching the ground. Here is where it touches the ground. So that's your angle of elevation. So that's my reference angle. Let's label our sides. Opposite the right angle is my hypotenuse. Opposite the 40-degree angle is the opposite leg. And the ground is touching the 40-degree angle. It's next to it, so that's the adjacent leg. So I believe there's two questions here. What is the horizontal distance? All right, so this is the horizontal side. So that's the ground. What is the horizontal distance from you? So they want to know what is the horizontal distance. And then the second question is how long is the kite string? That's the hypotenuse. So there's two questions. So the first one is what is the horizontal distance? So it says find horizontal distance. Find horizontal distance means find the length of the ground. That's the adjacent side. So that's the adjacent leg that we have to find. So I'm going to use the adjacent leg in combination with the 150 meters. That's the opposite side. So we're looking at the opposite side and the adjacent side. That is the tangent ratio. So tangent of 40 degrees is opposite over adjacent, and then set up your proportion and cross multiply. So here we have the variable x times tangent of 40 degrees equals 1 times 150, and then we have to divide away the tangent of 40 to get x by itself. So this is what we're typing into our calculator, 150 divided by tangent of 40 degrees. All right, so when we do that, we get 178.76. That's what I called x. I'll put x here on the diagram. We have to find the length of the string next, so I'll call that y. All right, so the second question then is, how long is the kite string? So we have to find the string length. In other words, we have to find the hypotenuse. So we have to find the hypotenuse, and again, we're going back and using the given information of 150 meters, which is on the opposite side. So we want to use the ratio created by the opposite and the hypotenuse. So that is the sine ratio. So sine of 40 degrees equals opposite over hypotenuse. Again, set up a proportion and cross multiply. So we have y times sine of 40 degrees equals 1 times 150. To get the y by itself, we have to divide away the sine 40 from both sides. So this is what we're typing into our calculator, 150 divided by sine of 40 degrees. All right, we'll do that. We get a pretty big number here. We have 233.36, and again, that is in meters. So here's our last example, and this is the biggest of them all because there's actually going to be not just one triangle, but two triangles. And so we're going to have a lot to diagram here. I'm already using a couple different colors, but just to kind of emphasize the two different triangles, if you got a second color or a highlighter, you might want to bring that in at this time because we're going to have two triangles layered on top of each other. It's going to be a lot of information to keep track of. Here's example 4. So you are standing on a 75-foot cliff looking out over the water. Okay, just pause for a moment. Here's the cliff. Here's the ground above. That's where you are standing, right on the edge. And then here's the water. All right, so again, we're just labeling some of these things. There you are, standing on the cliff. I guess it was 75 feet. We can put that information on there too. 75 feet above the water. So because we're trying to turn this into two sides of a triangle, we're making that cliff straight up and down as if it like came right to the edge of the water right there. So there's no sandy beach. It's just water right into a cliff. So you look down 12 degrees. Now, because you're looking down, that's your angle of depression, and you see a boat. Now again, remember, you have to have this horizontal reference line. And so you are looking down 12 degrees. It's a very small drop. Okay, so this is representing your sight line. This is what you are you're looking in this path. This is your sight line. So from this horizontal reference line, you drop your gaze 12 degrees, and that's your line of sight, and you see this boat. Okay. Now that's the first triangle. Now you look down 48 degrees, which means you are going to create a second triangle. So let's switch over to a second color here. We're still using the same horizontal reference line. We're dropping our gaze 48 degrees. All right, so there's my 48 degrees. And that's going to create a steeper sight line to another boat. All right, so I have this blue information, which is going to be on the blue triangle here. Okay, so there's my right angle. And then I have this green information, which is representing the larger triangle to that further boat. Okay, so in other words, our two triangles have the same height, but they have two different bases. Now, the ultimate question is, how far apart are the two boats? In other words, bringing in a third color here, that's what we want to know. How far apart are the two boats? So what you have to realize is that distance that I've just represented in that orange color, that does not belong on a right triangle. So we can't solve for it directly. We have to solve for the green triangle and the blue triangle, and then compare those distances to get the orange distance that we need. And that's what we're going to do. So here is my green triangle. So I'm pulling the triangles apart is what you're seeing me do. Okay, so this is my green triangle in miniature with that 75-foot cliff. I'm going to call this variable x, I guess. Let's call it x. And because we dropped our gaze 12 degrees, we can't use that information because that's on the outside. We need the angle on the inside. Remember, these add up to 90 degrees, so 90 minus 12 is 78. So that's what I need right here. So let's label the sides. Opposite the right angle is the hypotenuse. That's my line of sight. Opposite the 70-degree angles is the water line. That's the opposite. And then the 75 feet that you see right here, that is touching the 78-degree angle. So that's my adjacent leg. So we have to use the 75 feet, and we're trying to find the bottom edge. Why are we trying to find the bottom edge? Because we're trying to find the distance between the boats, which is on the horizontal side of the triangle. It has nothing to do with the slanted sight line of the triangle. So opposite side and adjacent side is the tangent ratio. So tangent of 78 degrees equals opposite over adjacent. Let's cross multiply. So x equals 75 times tangent of 78 degrees. And so this is a distance of, let's see, 352.85 feet. All right, so that's this distance on the original diagram. That's the big base of the green triangle. 352.85, and that's in feet. So now we're taking the blue triangle, and here's a miniature sketch of my blue triangle with a smaller base. The height is still 75 feet. There's my right angle. Let's use a different variable, so we're not using x again. Let's call this w. So this will be w down here. And this time, when we dropped our gaze, it was a 48-degree angle of depression. But we can't use that. It's on the outside of the triangle, so we need the inside angle. Again, these are complementary pair. They add up to 90 degrees. So 90 minus 48 gives me 42. That's my reference angle. Let's label all the sides. So opposite the right angle is the hypotenuse. Again, we don't want that side. Here is your adjacent side. The 75 feet is next to your reference angle of 42 degrees. That's your adjacent leg. And then the base of the triangle, the W that we're trying to find, that's on the opposite side. So again, we're trying to find the base of the triangle, the opposite leg, and we have the 75 feet to work with. So again, it's the same ratio of opposite and adjacent. So one more time, tangent of 42 degrees equals opposite over adjacent, and then we cross multiply. So W equals 75 times tangent of 42 degrees. So that will give me an answer of 67.53. 67.53 is on the picture now. So if you take a look at these two lengths, what we're trying to do is we're trying to figure out what is the distance between the boats here. It's a question mark on the picture, but let me give that another variable. Let's call that y. All right, so to find y, we're going to take the bigger base, 352.85, and we're going to subtract that smaller base of the smaller triangle, and that difference will be the distance between those two boats. So in our case, we have a result of 285.32. And again, don't forget the units in feet. So we really have three different answers. We have the answer that came from the large triangle, we had the answer that came from the smaller triangle, and then we subtracted those two and got our final answer, which is that horizontal distance between the two boats.